We are going to talk about the scalar product form of a vector. Okay, so the scalar product form has two main derivations. Okay, we are going to focus on both of them, and then we are going to apply that to do some questions so that we will have a clear understanding on what's happening here. So normally the scalar product form looks like this: r dot n is equals to d. Okay, so here r represents the position vector of a point on the plane. So if you draw a plane like this, okay, let's say this is the plane. Okay, let's say this is the plane. Okay, and this is the origin. Okay, we have the origin also with us. So this is I and J, K, and we have J. Okay, so this is the origin. So any point on the plane phi, okay, any point on the plane phi can be given as a position vector. Okay, and that position vector is called as R. Okay, and we know uh, what n represents here is the perpendicular vector to the given plane phi. Okay, so it can be anywhere. Okay, it can be here, it can be here, it can be here, it can be here, or it can be here. It doesn't matter as long as it is perpendicular to the given plane. Okay, as long as it is perpendicular to the given plane. We know plane is infinite, right? So even though I have drawn until this, we know the plane also expands until here. So this is what we call n. Okay, the direction is only what matters here. We don't care about the magnitude. Okay, we don't care about the magnitude of the perpendicular vector. Okay, we are just not perpendicular vector. We can call it perpendicular vector or normal vector. That's why we use the letter n. Okay, so we don't care about the magnitude. We only care about the direction. And as long as the direction is perpendicular to the given plane, we can use it to find the scalar product form of a plane. Okay, and this d is any constant. Okay, d is any constant that you can have. Okay, it's a number. Basically, it's a number. But yeah, that's what we call d. Okay, so this form has another representation. Okay, since we can represent r as x, y, and z. Okay, and let's say n can be represented as a, b, and c. The xyz coordinates can be given as a, b, c. Well, that is equals to d. Okay, so if you do the scalar product here, you will get ax plus by plus bz is equals to d. So the standard Cartesian equation of a plane can be given as ax plus by plus cz minus d is equals to 0. Okay, so this is the Cartesian equation that we derive from the given scalar product equation of a plane. Okay, now we will learn how we can come up with the scalar product form of a plane. So, how can we derive the scalar product form of the given plane? Okay, so what we have here is the plane phi, and this is the origin. Here I have represented the vector r, which is the position vector of the point on the plane, and n is the normal vector. Okay, n is the normal vector. So here we know this specific angle. Okay, this specific angle is perpendicular to the plane. Okay, so if I connect this triangle, okay, if I connect this triangle, and if I look at it from this perspective, okay, if I look at it from this perspective, I will have a right angle triangle. Okay, I will have a right angle triangle. So that's what I will have. Okay, so the hypotenuse will be the absolute value of the vector r. Okay, and the let's say this is the angle theta. Okay, so let's say this is the angle theta. Okay, so this is the angle theta. So this will be the adjacent side will be the absolute value of the normal vector. Okay, the absolute value of the normal vector. This is what we have here. Okay, so by using this, I can say r cos theta is equal, the absolute value of r into cos theta is equals to modulus of n. How can I come with this? Well, cos theta is equals to adjacent side over hypotenuse. So that will be modulus of n over modulus of r. So we can say r modulus of r cos theta is equals to modulus of n. Okay. Now let's say the distance between the origin, okay, the perpendicular distance between the origin and the plane can be given as simple d. Okay, let's say that is given as simple d. So which means that is equals to the modulus of n. Why? That's what we are considering here. The distance from the origin. The distance from the origin. So I can rewrite this equation. Okay, I can rewrite this equation. Modulus of r cos theta equals to modulus of n into d equals to modulus of r cos theta. Okay, so I have the right angle triangle and I have come with an important relationship. Okay, so this is what we have here. Okay, and now let's say the unit vector, okay, unit vector of n can be given as the can be given using this notation. Okay, so what I can do is, okay, we know since r, okay, we know that r dot n, the unit vector of n can be given as, okay, it can be given as r dot n can be given as modulus of r, okay, modulus of r into modulus of unit vector of n into cos theta, the angle between the vectors r and n. Okay, and we know since the unit vector of n is given as the notation here, okay, I can say that is equals to 1. The modulus of that is equals to 1. So r into 1 into cos theta. So this can be given as modulus of r into cos theta. So this will be equals to, from this equation, I can say this is equals to d. So this is the first equation that we are going to come up with, which is r dot unit vector of normal vector of unit vector of normal vector is equals to the perpendicular distance between the origin and the given plane. Okay, and we know, okay, and we know n is equals to lambda n. Okay, lambda into unit vector of n, because n is the perpendicular vector, the normal vector. It can have any magnitude such that lambda is a parametric value. Okay, so I can rewrite this here. Okay, so I will have r dot lambda n is equal to lambda d. Okay, we can say lambda d is a parametric value. We can say lambda d is equals to a parametric value. So this is how we come up with the equation r dot n is equals to d. There is also another way to come up with the scalar product form of a given vector. Okay, so let's do that also. So here we have, okay, here we have the plane phi. Okay, so let's say we have x here and we also have y here. Let's say this is any point, okay, any point on the plane that the position vector can be written down as r. Okay, so x is a point on the plane that we don't know, that's a variable point. Okay, this is the origin. Here we have I, here we have k, here we have b. Okay, and we know the point y. Let's say we know the point y. So oy can be given as y. Okay, oy can be given as y. Now let's find out xy. Okay, now let's find out xy. Okay, so xy can be given as y minus x. So since x is equal to r in this case, I will give it as y minus r. Now let's talk about the perpendicular vector. Okay, let's say this is the perpendicular vector n, or the normal vector n. So we know xy dot n is equal to 0. Why? N is a normal vector for the plane phi. Since it is normal vector for phi, it will also be normal vector for xy. Okay, so xy dot n is equal to 0. So xy can be rewritten as y minus r dot n is equal to 0. Okay, so this will give me y dot n minus r dot n is equals to 0. Okay, so if you rearrange this, you will get r dot n is equals to y dot n. Okay, so if you know a point on the vector, I mean on the plane, okay, if you know a point on the plane, and you also know the normal of the given plane, you can come up with an equation for a plane. Okay, since this is a scalar product, you will end up with a number, okay, a value. So that can be given as r dot n is equals to dE. Okay, and let's say n is given as ABC. Okay, so now you can come up with the Cartesian equation also. You can write down r as xyz and n as ABC, that is equals to d. So after you do the scalar product, you will get ax plus 1, then we have by plus by plus cz is equals to d. Okay, so let's say point A lies on plane phi, and that is given as 1 comma 2 comma 3. Okay, and n is equals to 3 4 5. Okay, is the perpendicular vector to the given plane. So the plane looks like this. Okay, so the plane looks like this. Here we have the origin. A lies here, and this is given as phi, and this is the perpendicular vector. Okay, so this is the perpendicular vector or the normal vector. So first of all, let's write down the normal form here, which says that A dot n is equals to R dot n. So let's write down the specific order. R dot n is equals to A dot n. R is xyz in this case, and n is given as 3, 4, and 5, and a is given as 1, 2, and 3, and n is, we know, 3, 4, and 5. So we have 3x plus 4y plus 5z is equal to 3 plus 8 plus 15. So that is equal to 26. So the Cartesian equation can be given as 3x plus 4y plus 5z is equals to 26. If you want to find the perpendicular distance between the origin and the given plane, okay, if you want to find the distance between the plane and the origin, what you have to do is you just have to first of all find out the unit vector of n. And we know how to find the unit vector. It's just n over modulus of n. That's all. So that will be equals to 1 over square root of 3 squared plus 4 squared plus 5 squared into n. So that is equal to 1 over square root of 9 plus 16 plus 25. So that is equal to 1 over square root of 50. Okay. So that is equal to 5 root 2, 1 over 5 root 2 n. So to find the perpendicular distance, we have to do r dot unit vector of n is equals to the perpendicular distance or the shortest distance. So that is equals to, well, for r, I can replace the value with 1, 2, and 3. So 1, 2, and 3. Modulus of n can be given as, let's write down n first. N is 3, 4, 5. Okay. And we have to write down that 1 over 5 plus 2 is equals to, we have d. D is what we have to find. So d will be equals to 1 over 5 root 2 into 1 into 3, 3 plus 8 plus 15. So d is equals to 1 over 5 root 2 into 26. So that will be equals to 13 root 2 over 5 by 1 over 5 into 2 to 26 into root 2. So this will be cancelled. So we will have 13 root 2 over 5. So we have to give it in units. Yeah. So the shortest distance between the origin and the plane can be given as 13 root 2 over 5. So what are the basic equations that we learned so far? R dot the unit vector of n is equals to the perpendicular distance between the origin and the plane. Okay. R dot n can be given as A dot n. Where A lies on the plane, which will reduce into a value. Okay. And then you can come up with the Cartesian equation. Ax plus by plus CZ is equals to D, where n is given as A, B, and C. So what I want to highlight here is that the coordinates of n will be the coefficients of x, y, and z respectively. Okay, so this is a small thing that you have to keep in mind. Okay.
Thanks for watching the 31st video in our vector series. If you found this explanation of the scalar product and Cartesian equations of a plane helpful, don't forget to like, share, and subscribe for more tutorials. Hit the bell icon to stay updated with our latest videos. Check out the full playlist to master vectors and follow us on Instagram. I'll see you in the next video. Until then, keep learning and stay curious. Bye bye.